Okay, nothing new in this one. This is just a little bit of practice using the simple harmonic motion equations that we've derived. Okay, just to see if you remember these equations, you might want to try and write them down, but remember they're on the data sheet, so you haven't got to memorise them. Just if you're familiar with them, it makes it a little bit easier to do the questions. So x against t, we need to know x equals a cos 2 pi ft. The maximum velocity equation, maximum velocity is 2 pi f a. The general equation for acceleration at any displacement, minus 2 pi f all squared times x. The maximum acceleration just when x is at its maximum, so 2 pi f squared times a. And the velocity equation, the velocity is minus 2 pi f a squared minus x squared all square rooted. Okay, so if you're familiar with those equations, it will make doing the questions quite a lot easier. But you also do need to apply a little bit of common sense and to think through the situations quite carefully. Okay, just to try and look at that again in terms of graphs, we've got x against t, which is our most familiar graph, our cosine relationship. We've got v against t, the gradient of that graph, which is a minus sine graph. We've got a against t, which is a minus cosine graph. So again, you'll see that you just have to multiply that by minus some constant number, and it will go from the first graph to the last graph. And then we've got a against x, which again, from our definition of SHM, is a proportional relationship but in the opposite direction, hence the negative gradient. Okay, so if we can do all those things, then we should be able to answer some questions. So let's have a look at the first one. This is a pendulum on a clock with a frequency of 2 Hz. You pull it back 10 centimeters and release it. How long does it take the pendulum to reach the center? Well, we don't need an equation for this. We need to work out that an entire oscillation, if the frequency is 2 Hz, the period will be half a second. So that's half a second to go there and come back. Okay, that's a quarter of a second to go there. That's only an eighth of a second to reach the center halfway there. To get the displacement a quarter of a second after it's released, well, again, as I said, it's half a second to get there and back, so it's a quarter of a second just to get there. So the displacement is minus 10. Just the trap there might be the minus sign. It's the opposite side to where it started from. The velocity as it passes through the center is the first time we need an equation. So this is a V max. So we've got V max is 2 pi fa, 2 times pi times the frequency is 2 Hz times the amplitude. If we turn it into meters, 0.1 meters. So it's going at 1.26 meters per second as it passes through the center. What's the acceleration as it passes through the middle? Well, you might be tempted to use an equation here, but when it's at the middle, the displacement is 0, and therefore the acceleration is 0. Okay, so you don't really need to put that. If you wanted to, you could put minus 2 pi f squared x, but your x value would be 0. Okay, its velocity when it's 5 centimeters from the center is probably the most tricky one. You might want to look at this and think, oh, it's going to be half at the middle, but that's not correct. Okay, we do need to use the equation, so 2 pi f times the square root of 0.1 squared minus 0.05 squared, because 5 centimeters is 0.05 meters, gives you 1.09 meters per second. Okay, some slightly trickier ones. So this time we've got a mass pulled down. It's got a period of 4 seconds and an amplitude of 0.12 meters. So its displacement 0.25 seconds after it's released. Well, now we do need the equation x equals a cos 2 pi ft. Here's our amplitude, 0.12 meters. Cos of 2 times pi times the frequency. Well, we got a period, so we need to do 1 over 4, 0.25 seconds. And then times t, 0.25. This gives us a displacement of 0.11 meters. Okay, how long will it take to reach a distance of 0.06 meters from the equilibrium position? Well, again, we're on x equals a cos 2 pi ft, but this time we're trying to find a value for t, so that makes the maths a little bit trickier. So I've got 0.06 is 0.12 cos of 2 pi ft. First step is to divide down by the 0.12, so I get 0.5 equals cos of this expression. Then the crucial step is to do cos minus 1, but make sure your calculator's in radians, otherwise you're going to find you get an angle in here in degrees. So that's a third of a 1/3 pi radians. So that's 2 pi times 0.25 t. So cancel out the pi's, divide the third by 2 times 0.5. You end up with 0.67 seconds. What displacement is velocity to be 0.1 meters? Well, now we're trying to find a displacement where the velocity, we've got a value for the velocity, so we need this equation, but again a bit trickier because our unknown is in here. So just put the numbers in. V is 0.12 pi f. Here's the amplitude, 0.12 meters times the displacement. Okay, what's that displacement going to be? Well, get your 2 pi times 0.25 over the other side. That becomes 0.064. You've got this complicated expression here, square rooted, so square both sides to get rid of the square root. Okay, then you've just got to take that over, and you end up with 0.01 meters. Then you've got to remember that's not x, that's x squared, so you need to take the square root, and you get 0.1 meters. Okay, I should have said meters squared there, 0.1 meters.